Perfect. Now I know I can go back. Okay. Well, thank you so much, Juliet, for the kind introduction and also hosting me here. It's really exciting to be back in Boulder. I've been really enjoying the interactions. It's never enough to see the exciting things that are happening here, and thank you for the hospitality. I'm going to talk a little bit about some of the work that we have been doing on nonlinear nanophotonic circuits today. So hopefully I'll give you a flavor of what each of those terms means and how we're envisioning the future of this direction. Before that, this is how my group looks like. Maybe I can turn down the light a little bit. Thank you. This is how my group looks like, and I've highlighted the people. Oh, they're perfect. Thank you. Who have actually, yeah, it looks great. Who have actually done the work. Mostly my senior graduate students, Ravi and Gordon, and also a number of my former group members, students and postdocs who have contributed to the results that I'll talk about. I'm also going to quickly give you a flavor of the things that I'm not going to talk too much about, but is related to the topic of this conversation. We are excited about looking at nonlinear resonators, individual nonlinear resonators, and studying their quadratic nonlinear dynamics. So one example is how solitons form because of quadratic nonlinearity as opposed to Kerr nonlinearity, which is the main approach for soliton generation. I'm not going to talk about that effort. Actually, Ming Chen is here as a postdoc, so if you want to learn about some of the work he has done on mid-infrared solitons, you should ask him. I'll touch on some of that a little bit in terms of how we look at a new nonlinear dynamical regime of these resonators in the talk, but I'll not talk about these results. A good portion of the efforts that we have been doing in my group is also based on networks of nonlinear resonators. So we have been looking at how to create a programmable network of nonlinear resonators and use them for different fundamental studies, going from looking at phase transitions to topological and non-Hermitian photonics, all the way to computing. So I will not talk about most of those results either. I'll touch on that a little bit, especially in terms of how we're bringing that set of efforts into on-chip and nanophotonic realization. Most of the talk, I'll try to focus on how we have been developing ultrafast optics in nanophotonic lithium niobate. So I'll try to zap through some of the results in these papers and show you the building blocks, how things have started, and hopefully give you a sense of where we're going from here. So let me just give you my perspective about nonlinearity, just to set the stage. And of course, the nonlinearity refers to the systems that are not linear. And the main characteristic of linear systems is that superposition holds. So you put a bunch of inputs, you get a bunch of outputs. If you put a superposition of those inputs, you get the superposition of those outputs. And a nonlinear system does not have that. And that sounds like a lot of systems. And that is true. And this is one of my favorite quotes from Ulam, which says, using a term like nonlinear science is like referring to the bulk of zoology as the study of non-elephant animals, because almost everything we pick is nonlinear, despite being comfortable mathematically with the linear system. From the physics and fundamental perspective, you can find nonlinear behaviors in all sorts of different sciences and technologies, going from biology to chemistry to different physical systems. This is an example of a social behavior, if you wish. But one of the important aspects of nonlinearity is how we can develop devices and how we can affect technologically in terms of what we do. And one of the biggest examples of a nonlinear process that have been essential for all the computing platforms we have known is the switching. And if you think about the electronic side and how switching came to being, one of the examples, so this is not the first example, one of the examples is how we figured out to do nonlinear processes with vacuum tubes. Then we figured out the semiconductor physics and how to build this kind of switching mechanisms with transistors. Then we build the integrated transistors. And that's really the foundation, the hardware foundation of what led to the digital revolution and just seeing everything we see today in terms of all the computers you have in your pocket and all the virtual friends we have made with all the chat GPT and alike systems. So one of the questions that we have been interested in is, if you think about one application of nonlinearity, which is computing, nonlinearity is essential for almost any meaningful computing platform. And the question that we're interested in is, how can we realize and utilize light for such nonlinear functions in a meaningful way, both on the fundamental side and also on the technological side. So let me give you a little more example in terms of computing. So maybe we can at least dig a little deeper and I show you my perspective on that. So when you think about why you want to use photonics for computing, one of the biggest answers that people talk about are the energy and bandwidth. And that's the challenge that we have been facing, and it's getting worse and worse. So one of the things that we have seen in the past few years is the evolution of the large language model. And if you think about how much it costs to just run the machine, this is an estimate, but apparently this is a conservative estimate in terms of how much it costs to just run the machine. Forget about how much the machine costs itself and how many of those machines we have. But there is an estimate that about 10% of the energy we're generating overall is going to the data center. And that number is not going to go down, it's just going to go up. So that's one of the reasons that photonics becomes attractive, at least from the motivation perspective, which is, can we solve the bandwidth and energy problems of the computing platforms? So I want to focus mostly on the speed problem, and I want to show you this graph, which is, one day I asked one of my students to look up the clock rate speeds of different CPUs that have been around, and he generated this plot. So according to him, any existing CPU is on this graph, and it shows the evolution of the clock rate as a function of year they were announced. And you can see that the clock rate grew exponentially back in the days, and then it kind of hit the ceiling. And 20 years ago, if you bought a computer, the CPU was probably 2 gigahertz. Today it's probably 3 gigahertz. So that number really hasn't changed. And it's not fundamental problem, but it's a very deep practical problem that is really hard to imagine that can be addressed without using photonics. So that's one of the motivations. Can we break that speed limitation of electronic computing, especially in terms of clock rate, with photonics? And one of the reasons that we are interested in thinking that photonics should be the solution is because photonics have a proven track record in communication. If you think about the coaxial cable and the amount of bandwidth you can put on the coaxial cable and the optical fiber, right, that problem is solved, and we have transitioned in terms of bandwidth and speed for the communication. The question is, can we utilize the same kind of speed and bandwidth, not just for the communication, but for the computing? The caveat is that for the communication, if you use an optical fiber, you only want to have a linear system, right? So nonlinearity is a bad thing. And that's the opposite for computing. So you actually need computing. You actually need nonlinearity for almost any computing. So that's why photonics has been, at least that's one of the biggest reasons that photonics have been facing a lot of challenges in realizing computing in a way that could be competitive with electronics. So photons don't interact with each other. unless you put them in some sort of material, such as my favorite material, which is lithium niobate. And then the photons start talking to each other. And that's how you can get effective nonlinear functions in the photonics. If you think about the bulk of integrated photonics, maybe in the past 2 decades or so, most of the photonic integrated circuits that people have been developing barely have nonlinearity. So the silicon photonics, the silicon nitride photonics, they're barely nonlinear. So that's why most of these devices and most of these circuits are equivalent to using resistors, capacitors, and inductors in the electronics world. So the nonlinear piece, or the equivalent of transistor, is still missing in the integrated photonics world. But nonlinear photonics has been around on the tabletop system, so there has been more than 60 years of history of building different systems in the tabletop. And there has been this transition, maybe in the past 5 or 10 years, bringing the functionalities of these tabletop systems into nanoscale devices. And there are 2 hopes in that direction. One is that you can get components and performances from the components that are better compared to the tabletop and bulk nonlinear optical system. And the second thing is a little more obvious, which is we miniaturize these systems. So the goal is that maybe we can create the same large-scale circuits in the integrated platform. So the same transition we saw in electronics in the past 80 years, which is, this is where we were with those vacuum tubes, and then this is where we are today, and how that integration helped the miniaturization and making larger and larger circuits. There is a hope that a similar thing will happen in the nonlinear photonic circuits. So that being said, the work that we have been doing is, at least the work that I'm going to talk about today, is exclusively focused on lithium niobate nanophotonics. There has been an exponential growth in utilizing lithium niobate nanophotonics, partly driven by the commercial availability of the thin film lithium niobate. So now you can get these wafers and start making devices on them, and this is what we have been doing. So you can etch waveguides and resonators and other linear components, and we have also been doing periodic polling for the nonlinear functions that I'll talk about a little bit for providing phase matching for these devices. So I'm not going to talk too much about how we fabricate these things, but the short story is that there are 2 steps: the polling, or the periodic polling, and then there's the waveguide fabrication. And we go through that and make these devices. But what I'm going to focus on and tell you a little bit about is the difference of most of the work that we have been doing with most of the other work that has been happening in lithium niobate is that we have been utilizing the ultra-short pulses in these circuits. So most of the experiments that I'm going to talk about, we start from femtosecond pulses. We build the circuit on lithium niobate nanophotonics. We get femtosecond pulses out. The experiment is not so nano. It still looks like a tabletop ultrafast optics experiment. There's a nanophotonic chip somewhere. It still is based on tabletop mode-like laser systems. I'll come back and talk about that in a little bit. But the idea is to create these circuits and build on that and build the whole system. So why are we so focused on these short pulses? Yes. So that's a great question. So lithium niobate in the bulk form, lithium niobate has a strong nonlinearity. So the chi2 is relatively high. It's not the strongest nonlinearity on the bulk materials. It turns out that, of course, the community have been looking at the largest nonlinearity and looking for figuring out what can have the largest nonlinearity coefficient. Lithium niobate is probably not even on the top 10. The combination of having lower other nonlinearities, such as Raman, 2-photon absorption, even photorefractive effect, so that you can get the actual nonlinear process that you look for, and also the transparency window is a combination that made lithium niobate successful in nonlinear optics. In addition to that is the wafer scale thin film lithium niobate development. So this combination of being able to pull, being able to access this nonlinearity, despite not being the strongest nonlinearity, and also having access to the thin film wafers, that makes it now ready for the kind of work that I'm going to talk about. There are other materials that are being developed. I think there's a lot of great work on 3.5 materials. Still hasn't got to the same level of material readiness for these efforts. If that makes sense. Yes, so that's the second order. So the polarization, so yeah, E squared, that's right. So the polarizability is chi2 times E squared. And this is, depending on how you look at it, what I can say, it can be a few orders of magnitude stronger than the chi3. So chi3 exists in all materials. Chi2 only exists in the non-center symmetric materials. But if you have the non-center symmetric material, you can have a much stronger nonlinear behavior compared to chi3. And it's not apple-to-apple comparison, but you can define an apple-to-apple metric. Good? So the P is equal, yes, chi1 times E, chi2 times E squared, chi3 times E cubed. Well, it's E squared. Yeah, the Kerr effect is index dependence on intensity.
That's why you say the chi3 intensity piece is all independent.
That's right. Good. So we're good on the fundamentals? Okay. So why do I insist on short pulses and few cycle operation? And one of the biggest things about quadratic nonlinearity, parametric nonlinearity, including the chi2, is that if you look at the, for instance, gain or the strength of this nonlinear process, it depends exponentially on the square root of the peak power. So everything is about the peak power. It's about your field. So if you have the same average power, but you can make your energy squeeze into short pulses, you can have a much higher peak power, and that much higher peak power can lead exponentially to much stronger nonlinear performance. And that's one of the reasons that you can benefit from operating with short pulses. That's on the temporal side. You use nanophotonics, you also confine your light spatially in these submicron modes. That's why we're dealing with nanophotonics. So this is submicron mode structures. So this combination of spatial and temporal confinement is something that didn't really exist in the other chi2 platforms. And now you can access much larger peak powers for the same low average powers, and that can give you much more efficient nonlinear processing. So I'll come back to it and show you how this actually even holds in the quantum regime. So even if you have a single photon, but you make sure it's confined in time and in space, you can actually get much stronger nonlinear behavior in the same material system compared to the broader wave function in time. So the other reason that we are focused on short pulses is that we are using what we call the time division multiplexing. So I'll talk a little in depth about it later in the talk, hopefully. And the idea is that we put pieces of information in time bins or in short pulses. So that's how we split our time bin into or time slot, or the length of the cavity, for instance, into smaller bins in the time domain. And that's how we utilize our spectrum, meaning that if we have a shorter pulse, we can use a much broader spectrum. So the broader the spectrum, the shorter the pulse, we can fit more of these these temporal bins in a given length or a given time window. So this is in contrast to the frequency division multiplexing, where you take a broad spectrum, and then you take that broad spectrum and you split it into spectral chunks. So when you do that, you take the average power that you have in that spectrum, and you divide it by the number of bins that you're splitting it into. So that means that by definition, you're losing that peak power advantage for nonlinearity. So in the telecommunication world, the standard practice for multiplexing is the frequency division multiplexing, or the wavelength division multiplexing. So you put each channel on a different wavelength. And that's actually beneficial because you want to be in the linear regime in the communication channel. If you want to use the nonlinearity, if you do that, you're going to get that hit by the peak power. So you're going to divide your power by n, and you wouldn't be able to utilize that nonlinearity efficiently. So that's why, for us, this combination of confining the light temporally and being able to utilize these temporal bins is actually extremely useful to be able to develop computing and information processing systems. Okay, let me tell you what is this magical nonlinear process that I'm going to talk about. So a 10-second refresher on nonlinear optics. The one and only process that I'll talk about today is optical parametric amplification. And I want to encourage you to think about it as equivalent of transistors in electronics. Not so much about the actual functionality, although there are similarities, but mostly about the universality. And hopefully I'll make that case by going through the examples that I'll show. But what it is that when you use a Chi2 platform and you start with pump photons at the pump frequency, and you have the right phase matching, you can split these photons into two identical photons at half frequency of the pump. So that's what we call the degenerate optical parametric amplification process, or the degenerate parametric downconversion process. This is a phase-sensitive process, meaning that if you want to get the pump energy to go to the signal and amplify that signal, you need to have a specific phase relationship between the signal and pump. So that way you take energy from pump to the signal. If you add pi to that phase relationship, you're going to reverse the flow of energy. So you're going to go from your signal to the pump. And that's what people call second harmonic generation. So second harmonic generation, optical parametric amplification, they're two sides of the same coin. And this is something that has been around in the community for a long time. It is known as a noiseless amplification mechanism. So that's why it has been very helpful for quantum optics, for generation of squeezed vacuum, for instance. I'll talk about that a little later. And also for coherent communication scheme. We have also been using it for computing, so hopefully I'll touch on some of those applications a little more as well. It has been around on bulk OPAs for more than 60 years. The problem has been, if you wanted to get sufficient gains out of bulk crystals, you usually needed large lasers and high enough pulse energy or powers to be able to get meaningful gains in the bulk. And your bandwidth also would be limited by the dispersion property of your material. So those are the things that would actually change when you go to nanophotonic lithium niobate. And I'll show you how we can create those and how we can build circuits using that nonlinear component. So the first and most important thing is what I talked about in terms of the spatial-temporal confinement of your light. And this is the example to just show you how that works in a simple periodically poled lithium niobate waveguide. So the idea is that if you change the cross-section geometry of your waveguide, you're changing your dispersion. And each of these cross-sections correspond to a slightly different dispersion relationship. So the top one corresponds to having no groove velocity dispersion for the pump and signal, and no groove velocity mismatch between the pump and signal. That leads to the largest magnitude gain and the broadest spectrum for the gain. If you change the geometry a little bit, you lose a little bit of groove velocity dispersion. That corresponds to losing bandwidth. You lose a little bit of groove velocity mismatch. You lose a lot of magnitude gain. So I'm talking about 15 to 20 dB difference in the actual gain that we're looking at. So this is a substantial difference in terms of being able to get large enough gain and broad enough bandwidth. And it turns out that we can do that relatively simply in lithium niobate by just picking the right geometry. So we have been mostly focused on pump at 1 micron, signal at 2 micron, because it happens to be a very easy regime of operation in this zero growth velocity dispersion, zero growth velocity mismatch. And the first experiment we did was to just make that OPA, a single pass OPA, and try to look at how much gain we get. So I'm showing the gain in terms of dB per unit length, and also the bandwidth on the x-axis. And I'm comparing the gain with all the other integrated photonic gain mechanisms. So there's the forward mixing, which is the Chi3. There's the semiconductor optical amplifiers. So those are known to be the largest gain mechanisms in integrated photonics. And then there are some other mechanisms that I will not talk about. And this is how our first initial results look like. This is where we are today. So in terms of bandwidth, in terms of magnitude of gain per unit length, it's more than you hope for. So you don't have any limit in terms of how much gain you need or how much bandwidth you need. So you can now have a lot of gain and use very short pulses and start thinking about building circuits. Now, one of the first things we did was, okay, so we have gain, so what? So we started thinking about how we can utilize that OPA, not just as a gain, but as a switching mechanism. So we started building a small-scale circuit using the OPA to be able to show something as a switching mechanism that could be useful for the clock rate limit of computing platforms. And this is one of the small-scale circuits we designed. And I'll show you in the next slide how it actually looks like. So the idea is that we have a simple straight waveguide. It has periodic polling on one side, and we combine it with this directional coupler. So the feature of this waveguide is that it has what we call the polling defect. So what happens in just the straight waveguide is that when you start going through the waveguide at the beginning, the phase matching is for second harmonic generation. So you start with the fundamental, you start generating a little bit of second harmonic generation. The coupler is designed to drop most of the fundamental input and take it to the drop output. So when you are in the low energy regime, the second harmonic generation is very inefficient. So most of your energy is still in the fundamental, and it's going to get dumped into this drop port. So most of your input is going to be routed to this drop port at the output because of the linear response of the directional coupler. If you start increasing the pulse energy, now your second harmonic generation becomes more and more efficient. So now when you get to the coupler doesn't see much of the fundamental. It sees mostly the second harmonic. The second harmonic has a shorter wavelength, so the coupler doesn't really act on it. So it keeps going through, it doesn't get dumped. The polling defect flips the relative phase of your second harmonic and fundamental. So instead of going more second harmonic generation, you're going to reverse the energy flow back to OPA. And that means that your energy is now going to go back from second harmonic generation to the fundamental. So that's the role of the polling effect. And then at the output, you're going to get your fundamental frequency input recovered in the output. So we did this experiment just to show that this actually works. One of the reasons we designed it is not to do computing. It was to make a satchel absorber for mode-life lasers, which I'll talk about a little later. But it turned out that this is the fastest switch, the lowest energy, or the highest energy bandwidth efficiency for an all-optical switch. And then we decided to just publish that. So in terms of the speed, the reason we get this fast operation is that the nonlinearity is instantaneous. It's the Chi2 nonlinearity. There is no cavity involved, right? So you don't need to worry about the lifetime in the cavity. It's just a traveling wave. So the only thing that limits the speed is the dispersion engineering. 50 femtosecond is what we actually measured. We think we can easily get to 10, even with the same design we had, but we didn't have any tool to actually show it. But nevertheless, that's the kind of switching, excuse me, that you can do with this kind of OPA-based circuits. We have done another example. I'll not talk about it more, but it's the same OPA doing a different nonlinear function for computing, in this case for deep neural networks. So we created what people call the rectified unit, which is basically just giving you 0 if you have negative field, and then linear response when you have positive field. We can do this with the same OPA process. We did the experiment. This is the comparison plot I want to show you, which is showing how much energy you need to get that nonlinearity happening. So how much energy you need to be able to get this nonlinear response. And this is how much time you need for this process to happen. So how fast is this switching fundamentally? And you want to be in that corner. So you want to have a low energy per activation, and you want it to happen very fast. This is how CMOS electronics lie now. So this is that few gigahertz activation function speed, which is limited mostly by the electronic connections. The energy is pretty low. We had to estimate this energy. By the way, nobody gives you that energy per transistor, but this is what we could estimate based on the numbers existing. This is what most of the optical or electro-optical processes are in terms of the energy and the bandwidth or the speed you can get. And this is what you can do with just a single OPA. So you can clearly break this time bandwidth product in terms of where you are, even compared to electronics. So the speed is a given, right? This is a traveling wave process. It's instantaneous nonlinearity. As long as you do the phase matching and you do the dispersion engineering right, you're going to get an ultra-fast response. The energy is something that is still not getting to where we are with the transistor. The biggest and most important question is that this is just a single operation. How can we utilize it in an actual meaningful computing, right? So it's not justified to just say, I can make the best transistor ever if I can't put it in a circuit and do the things that people can do with a circuit. So this is another question that we have been also looking at. And we have put just this paper on arXiv very recently to show not the nanophotonic realization, but the bulk discrete component kind of realization of using the same kind of Chi2 nonlinearity in a traveling wave, and show you can get to the 100 gigahertz and more than 100 gigahertz. That 100 gigahertz experiment is limited by the equipment we have. We can actually build a computer, do computing at the clock rates that are more than 100 gigahertz, and that shows a path on how you can basically build the circuits that you can't build with electronics. Yes.
You know, whether it's or the process of doing the defect, so there is either 0 defect. Is that applied? What is, how do you do that?
So there's a bias here. So we have this omega. So the signal is the second harmonic. And then we put a bias signal, which is at the half of that signal frequency. So the phase is defined by the phase of that signal at half frequency. So if, that's right. And that's exactly the going from second harmonic to OPA. What we choose, well, basically what you need is if it is negative, you want to make sure it just converts back to the fundamental. But when it is positive phase, you want to make sure that you get more and more as you increase the pulse energy. So it goes into amplification mechanics. So no, because the defect case was we didn't have 2 inputs. So the defect case was we only had the fundamental. So we start with second. When you don't have 2 inputs, and you start with the fundamental, you just get second harmonic energy. And the defect was to flip that. Yeah. So the biggest question about this, which we try to answer a little bit here, is how to use this component in a computer. And that's the paper. Yeah. Yeah, no, that's an excellent question. So I break it into two questions, right? So one is digital versus analog, because it's not really the transistor, it's the digital nature of digital computing that will give you that error correction that you have separate. So we do have digital systems that we can build based on the system. So a lot of the work we have been doing on the icing machine is based on binary phase. And then there is that built-in error correction we have. But then there's the analog version. And the analog version, that's always the case that when you have no noise, you can do infinite power computing with the smallest system you can imagine, but there's noise always, and then you need to deal with that. We have looked at different architectures of analog computing, including cellular automata. And I'm not talking about most of the computing work we have done, so that's why I don't go deep in that. So we have shown some robustness in cellular automata. Neural networks, in some cases they're robust, in some cases they're terrible in terms of noise. So you're right that that's one of the pieces in the whole equation that we need to look at. Okay, so that's a good question. So modulate might not be the right word because you imply electric modulation. So the way we're thinking about building these systems, and that's how we did it in this 100 gigahertz computing, again, which is, I'm not going to talk about it, but we're using 100 gigahertz clock rate computing, and we're only using 10 gigahertz modulators in our system. So this is, again, the beauty of time multiplexing. So I'll come back talk a little bit about time multiplexing, but you can make really short pulses, and then you can interleave them in time domain. And that way, your speed can be still very fast because it's all about how accurately you can do the timing, not how fast you can modulate. So if I can modulate 10 gigahertz, but I have 100 femtosecond, and I can put another 100 femtosecond next to it with enough accuracy, I don't need a 100 terahertz modulator, right? So that's kind of the trick we're playing. So it's not really limited by the modulator, it's limited by how well we can do the dispersion engineering and how well we can put the pulses next to each other. Okay, I think there was one more question. Good. Okay. So computing, it works. At least it works on the component level, and it works on some scale of system level. I want to show you a little bit of how we do things on the quantum side. So maybe I can just go through this a little faster so I can get to some other aspects of the work. So this is how we built a small-scale circuit to do squeezing using short pulses, using the same OPA. So again, the same building block, a slightly more complicated circuit. So we have the first OPA here, it has about 10 dB of gain. That's how you can generate squeeze vacuum. So basically, you pump it, vacuum goes in at the signal, you have phase-sensitive amplification, you squeeze in one quadrature, anti-squeeze in the other quadrature. So you have this 10 dB squeeze state. We use a second OPA, and we amplify it much harder. And what the second OPA does is you go from this microscopic quantum state, which is in the average number of 2 photons, to a macroscopic state, which can be 10 to the 3 to 10 to the 5 photons. And you can control the phase of the pump for that OPA. And if it is aligned to the squeezing quadrature, you get more photons. If it is not aligned, it's aligned to the other quadrature, you get less photons. But the beauty of this scheme, which we didn't invent, by the way, but it made a lot of sense to do it on the chip in nanophotonics, is that it makes your detection loss tolerant. So any loss you occur after this second amplification, your measurement is not sensitive to it. At least it's not as sensitive as you were if you do it with the microscopic state. So we did this experiment. We showed that we can measure about 5 dB of squeezing. This is how it compares with the other nanophotonic squeezing experiments. There's this DARPA project. I keep making this joke that we'll wait to see if they can beat this number. Scott, good luck with that. But I think one of the biggest reasons that we could get this number was that second OPA that makes your measurement much more relaxed in terms of loss. And also, it's kind of an all-optical measurement as opposed to balanced homodyne measurement. So you access the whole optical bandwidth, which is in the terahertz region. So we are trying to build on this, that the OPA generating squeeze state in the Gaussian regime. And we have been thinking, how can we use this to detect single photons? So can we just put a single photon into OPA, amplify the hell out of it, and use a classical detector, and just do the click detection with that classical detector? So this is the topic we looked into. And we did some measurements on that. I'm not going to talk too much about it. The bottom line of that experiment is that it doesn't work as well. It doesn't work in a useful way. It works to some extent. You get some efficiency, which is non-zero, and you get some relatively large dark count rate. You can't really create non-Gaussian states out of this kind of detection scheme. So we started thinking a little harder, especially with some of our theorist collaborators, to see what will happen if the nonlinearity is a few orders of magnitude stronger. Only a few orders of magnitude stronger. And it turns out that, well, if you are about 1 order of magnitude stronger nonlinearity, you start seeing some features in the OPA, which is the back and forth conversion happening in the low photon number regime. And if you do the right measurement, so instead of just using a click detector and say, I just look at the threshold, if the value of the voltage is above something, I say click. If not, I say no click. If instead of doing that, you use a homodyne detector on your pump, and you say, if I see this value in this range for the pump homodyne detection, I say there was a single photon, you can actually do much better in the order of 80% detection efficiency. And the reason is that this is actually a non-Gaussian operation coming from the OPA by just going 1 order of magnitude stronger nonlinearity. And that gives you a way to eliminate SNSPDs. Rich, how are you? And then think about how we can do these things even with the room temperature operation, the building ultrafast quantum information processing at room temperature operation. We are about an order of magnitude away in terms of experimental values. How do we get there? We'll make the pulses shorter, make the waveguides longer, make the dispersion engineering better. As easy as that, you know. The rest is what the graduate students will figure out. But that's basically what's going to happen. So I want to switch gear and tell you a little bit about how we're making circuits. And Juliet, how am I doing time-wise? OK, so I have an hour left. OK. So in the remaining hour, I'm going to tell you how we're going to make large circuits. And this is mostly inspired by the work we have been doing on the tabletop experiments. So again, the kind of experiments that I'm not going to talk about, but it's all based on building networks of optical parametric oscillators. So that brings me to OPOs, the optical parametric oscillators. I was talking to Juliet about this. So Bob Beyer, my PhD advisor, he was one of the people who did his grad school, and his aim was to build the first ever OPO. His advisor was Steve Harris, and he failed on that. So he was the second person who made an OPO. And there has been a lot of work happening. So this is 1964, 1965. A lot of work happening in OPOs. When I was doing my PhD with OPOs, he told me, I don't believe there's anything new you can do with the OPOs. And we did the icing machine work with OPOs, and he was like, I'm surprised there are still new things you can do with OPOs. And the OPOs today, they're still surprising me. So hopefully I'll give you a sense of how surprising these operational regimes of OPOs are, both on the classical side and the quantum side. And I'll show you how we're building our circuits based on those. But that's how I started building my career, you know. My PhD advisor telling me there's nothing new you can do with this. It has been around for 50 years. And I'm like, man, okay, let's see about that. So this OPO, the idea is the same OPA that I talked about inside a resonator. So the resonator is only for the signal in this case. So we make these on chip with lithium niobate nanophotonics. We have been doing a lot of experiments on using them as sources. So we have done CW operation. So on a single chip, we have shown you can go from 1.5 micron to 3.3 micron. We have done tunable combs. We pump the OPO with a picosecond comb. You generate picosecond signal idler. You can tune it again, all the way from visible, in this case, to about 3.3 micron. So I'm going to talk a little more about this ultra-broadband frequency comb that we generate with these OPOs. But I also mentioned that there is a startup from my lab. So basically, the students who did all that work are now graduated, and they're trying to commercialize these OPOs. PIC is photonic integrated circuit. I'll let you guess what that N is. They let me show this picture. They didn't let me show you what is inside. There's wire going into this box, fiber coming out, has something to do with OPOs. That's all I tell you, but it is commercially available per se. So again, you can buy these things now. So I want to talk a little more about how we do this ultra broad frequency comb inside an OPO, maybe in the next slide. But in the quantum regime, so that's on the classical side. In the quantum regime, one of the biggest theoretical questions that people have looked into is, can we generate deterministic Schrödinger's cat states with this OPO? That question, again, has been around for a long time. People theoretically looked at it back in the days, and the answer was, with the current technology, it's unlikely. That is still true. But the nanophotonics has brought up new opportunities. So this is a review paper we wrote with Hideo Mabuchi's group at Stanford to predict the evolution of the nonlinearity and how it could bring us to less number of photons. So that's what is shown in the x-axis, using this integrated photonic platform and using the short pulses. So this is where we are today. So this is one of the OPOs we built. Just to put some perspective here, this OPO has about 10 to the 4 photon threshold. So we want to get to sub-photon threshold. That's what the cat state ultimately gives you. The round trip loss in the cavity is in the order of 10 dB. So most of you who have built cavities don't even call this a cavity. But it still works as an OPO, and it still has the lowest threshold OPO, so it's in the femtojoule regime. So that shows you how much room exists on the material processing, on the design, to actually improve that. And that's where we want to be. So this is still ongoing, so we're trying to get things going in that direction. But currently, most of our efforts in the quantum regime is creating non-Gaussian states with the heralded single photon detection. So I'm not going to talk too much about that. But let me show you the ultra broadband frequency comb. So this is one of the other new surprises from the OPOs that I wasn't expecting to see. So I told the same thing to my students, that I can't believe we can still find a new operational regime of the OPOs. So this OPO is a long cavity on the chip. So it's a poled lithium niobate waveguide. The round trip time in the cavity is 4 nanoseconds, half a meter long. It's designed to be pumped with a 250 megahertz femtosecond source. So the thing we see in the OPO operation is summarized in this picture, which is showing the spectrum as a function of pump pulse energy. So when you're below the threshold, so you just see the pump, you start going above the oscillation threshold, that's about 2 times above threshold. You start seeing your signal at half harmonic, so this is your pump wavelength. You get the signal wavelength at twice that wavelength. You also get some parasitic second harmonic generation. What was known, and we have done actually a lot of work on that, was if you crank up the power or the pump pulse energy, you get into this regime which is people calling chaotic OPO operation regime. So instead of seeing only one nice frequency comb coming out, you start seeing multiple frequency combs. So it's because of the mode competition. And that's what is shown with these lines under this broad spectrum. What we didn't know, and we saw experimentally first, and it took us a few months to actually figure out theoretically, was that if you keep pushing this pumping, you get into this regime that the coherence is reestablished. So we started looking at the temporal evolution of the pulses. So these are simulations. And we could see that, well, you start from long pulses, you generate the coherent output pulses in this coherent regime, and then you start seeing the incoherent operation. So if you look at the pulse-to-pulse operation per round trip, each pulse looks different when you get to this chaotic regime. But at some point, you start seeing this temporal self-cleaning, and what it means is that the spectrum or the temporal field shape, it cleans itself in a well-established and coherent and repetitive structure. So this is similar to what happens in the spatial self-cleaning mechanism in the Chi-3 multimode waveguides. Similar in terms of the behavior, the nature, it's completely different. So it took us a long time to be able to establish this understanding. We even measured those pulses. I don't have the pulse results, so we were seeing all sorts of 7 femtosecond features in the actual output in the steady state. But one of the things I want to show you, which is making this exciting in terms of frequency comb sources, is that if you look at the spectral broadening mechanisms in nanophotonics or even non-nanophotonics, you look at how much pulse energy you need to make broad spectrum, there are different mechanisms for making broad spectrum, including the standard supercontinuum generation using Chi-3 waveguides or optical fibers. These are some of the single-pass Chi-2 waveguides that we have been working on, including the work we have been doing with Scott Diddams, which was actually focused mostly on generating the visible side of the spectrum. This is another work that we have been doing to just minimize the energy, but not really optimizing the visible side of the spectrum. So again, they're commercially available, if you wish. And we have been looking into that regime harder and harder to see what is really the mechanism. So if you're surprised with the actual complexity of the dynamics that happens, we just went back to the OPA. We said, let's forget about the OPO for now, look at the OPA itself and see how things happen when you design the dispersion right. So this is what we call the soliton compression. Again, we don't call it. Actually, it exists in the literature, in the theory literature. People haven't really been able to get to this pulse length before. And what it is that you can start with a fundamental pulse. You can just design the dispersion right, and the phase matching is for the same OPA process, but you're starting from the fundamental, not the pump. And then you're going to generate second harmonic generation as it propagates through the waveguide. And because this is very efficient, you can go second harmonic generation, and you can go back to fundamental, second harmonic, back to fundamental. With the right dispersion engineering, you get to this regime that it looks like you have a short pulse not changing its shape, and a short pulse not changing its shape in the second harmonic. So you have a locked soliton in the signal, locked soliton in the pump. We did the experiment. We measured this. This is how the actual chip looks like, and I can actually see the back and forth conversion coming from the parasitic second harmonic generation. We measured barely 2 cycle pulses at the fundamental, which is 2 micron here. We did simulations. We expect to see maybe 7 femtosecond pulses. We were seeing about 13 femtosecond pulses. If you combine the second harmonic and fundamental, you get something in the order of 7 femtosecond pulse. In the simulations, you expect to get something that is sub or single cycle. So we still haven't been able to do that measurement. We think it's actually what is happening in the experiment, that we were actually in that regime, but we can't really measure it with all the tools we have yet. But nevertheless, even a single OPA, you can start from, actually we have done simulation, you can start from picosecond pulses. and get to this single cycle regime. And one of the other things we figured out is that you can use a very simple circuit and do pulse synthesis. And what it means is that if I put an electro-optic modulator and I put a picosecond pulse in, and I go through this soliton pulse compression, so I can get something in the order of single cycle, but I can also control the actual shape of that pulse, going from sine to cosine, by just controlling that electro-optic modulator. So this is substantially simpler than how we have been doing single cycle synthesis in experiments, which I guess some of you probably have been doing that on these high energy or high field experiments. So one of the motivations for this is, can we get into the extreme nonlinear optics regime? So can we do things like high harmonic generation and even things that are not just perturbative nonlinear optics? So I say only an order of magnitude. Maybe it's 2. But again, that's something that grad students will figure out. So, but that's the perspective. And I think this is, even if we don't get to the extreme nonlinear optics regime, the capability of being able to control these pulses in the sub-femtosecond scale is something that we didn't have access to before. So I know that I'm almost at the hour. I'm going to skip it. I'll just show you this. This is one of my former grad students who worked on some of these tabletop experiments that we have been doing with the OPO networks and also the linear and nonlinear resonator networks. These were mostly built using optical fiber technologies. That's why you see the mess of fiber on the table, the mess of cables, which are going to control these electro-optic modulators to control the couplings of these resonators. So he posed this way to remind you of this picture back in the days from the vacuum tube. So the goal is that we would like to bring all of these experiments that we have been doing in the tabletop to the nanophotonics. So I'm not going to tell you how we're doing that, but that's also happening. So I've already shown that you can make 70 independent resonators on a single chip. And we're going to look into that. So I told you at the beginning that almost all of the experiments I showed you are based on mode-lock lasers, and all of them are using the tabletop mode-lock lasers. We have recently shown that you can actually build mode-lock lasers on the same platform. So this is probably the quickest and dirtiest way of making a mode-lock laser. But for better or worse, it ended up in the cover of Science. And the numbers are not as appealing as fiber-based mode-lock lasers. But the pulse energies and the peak powers we get out of them are actually sufficient to pump almost all the OPOs and OPAs that I showed you previously. So of course, we're working on the mode-lock laser scheme. We're making passively mode-lock lasers and making higher pulse energy and shorter pulses in the platform. But the vision is that the sources and all the circuits, they all can live on the same monolithic platform. And that way you can build classical and also quantum processors on this platform. So that being said, I'll just summarize, show you some of these pictures. We have been working mostly on the small scale circuits and components. And now we're working towards building larger scale systems and circuits in this platform. And I stop here and thank you for your attention.